Hello there, Mr. Sutton here, bringing you the AB Calculus 5.5 homework solutions on RAM Part 2.
For number 1, we want to know if approximating this with LRAM is going to under or overestimate the integral. So we need to figure out if this is increasing or decreasing first off. So let's get our first derivative. That would be negative 4x minus 8. And we need to figure out if this is increasing or decreasing across the entire interval. So let's get the critical values and see where those fall. Factoring out a negative 4, I've got x plus 2. And then setting each of these equal to 0, we just have x equals negative 2 for the only critical value. Since that occurs at one of the boundaries of the interval, but not in between, that means that we're going to be consistently one thing or another inside this interval. All right, let's test a point in the interval. I think negative 3 would work out best. If I plug negative 3 into my first derivative, that's going to give me, let's see here, this is going to be a negative out here, negative in here, so that's a positive overall. That means this is an increasing function inside this interval. Since it's increasing, that means LRAM is going to under-approximate it. For number 2, we're trying to determine if approximating this integral with LRAM is going to under or overestimate it. So for that, we need to know if this is an increasing or decreasing function inside this interval. Let's start by taking our first derivative. So if we think of this as 4 times x to the negative 3, this ends up as negative 12x to the negative 4th. So if we find the critical values on this, setting that equal to 0 with the x to the 4th on the bottom, the only critical value is going to happen at 0, which is nowhere near this interval. So that means whatever values we test inside this interval are going to be a good representative of the entire interval. Okay, let's plug in a number between negative 10 and negative 6. So if I plug in negative 8 in this, that's going to give me a positive down here, a negative up here. So overall, this is going to be a negative result. That means since we are decreasing inside this interval, that LRAM is going to over-approximate. For number 3, I want to know if RRAM is going to under or overestimate this function's integral on the interval from negative 4 to negative 1. So let's test the first derivative on this to see if this is increasing or decreasing within this interval. So that'll be 8x to the negative 1/3. And I want to figure out where my critical values are just to make sure that this interval isn't getting split up between increasing and decreasing. So setting this equal to 0, I have 8 over, this will be the cube root of x. Now the only critical value I'm going to get out of this is 0 because that makes this undefined. And 0 is not in the interval from negative 4 to negative 1. So whatever we end up testing in here, it's going to be all of one thing, either increasing or decreasing. Okay, let's test a number in there. If I test out negative 2, for example, so that's going to give me a negative down here, positive up here, so I've got a negative overall. Since that means I have a decreasing function, that means that RRAM is going to underestimate this. For number 4, we're being asked to convert this integral to a Riemann sum. So I'm going to start by giving it the general format here. We want the limit as n approaches infinity of the sum from 1 to n of f of xi times delta x. And we have to figure out xi and delta x here. Easiest thing to figure out in the beginning is the delta x. So that's just going to be the interval length divided by n. So that's going to be 4 minus 0, or b minus a over n. So 4 minus 0 over n is just 4 over n. Next, for xi, that's just going to be the a value plus the I times the delta x. So this is going to be 0 plus 4i over n. Next, xi is getting cubed up here. That's our function, is the cubing function. So we need to do essentially 4i over n cubed times delta x here. That's just going to be, again, 4 over n. And we put all that inside that limit summation formation there. For number 5, we're trying to convert this integral into Riemann sum notation. So we need the limit as n approaches infinity of the sum from 1 to n of f of xi times delta x. That's our general form. and we have to figure out delta x and xi here and apply the f function to it. So let's start with delta x. In general, that's going to be b minus a over n. You're just taking your interval length and dividing it into n pieces. So this is going to be 5 plus 2 over n, or 7n. Next, for xi, in general, that's the a value plus I times delta x. So our a value here is negative 2. So we've got negative 2 plus I times 7 over n, or negative 2 plus 7i over n. So this whole thing is xi. So what are we doing to xi? Well, x is an exponent, so we're doing 5 times e to the all of this stuff. That's our f of xi term. Delta x again was just 7 over n. So putting it all together, we have 5 times e to the all of this stuff times 7 over n inside our limit summation notation. For number 6, we're trying to express this Riemann sum as a definite integral. So definite integrals, in general, look like this. We have an integral from a to b of f of x dx. The a value is going to be whatever is being added to the basically the delta x times k term in here. So that's going to be this pi over 2 term for our a value. And for the b value, we need to figure out how long the interval is. So the interval length is this delta x part over here that's being divided by n. So since pi over 2 is being divided by n, pi over 2 is the length of the interval. To get the b value then, we need the starting limit of integration, pi over 2, plus the pi over 2 that is the interval length. So pi over 2 plus another pi over 2 just gives us pi. And the function then is just going to be whatever is happening to the a plus pi over 2n in here, or pi over 2nk. So that's just cosine is happening to all of this. So we're going to have the interval from pi over 2 to pi of cosine of x dx. For number 7, we're trying to convert this Riemann sum into a definite integral. So put this in the form of integral from a to b of f of x dx. So the a value, this is going to be whatever is being added to the delta x, I. So that's this 2 in here that's being added to 3i over n. This 3 over n is just delta x. So this delta xi plus a is what we have inside here. So we have an a value of 2 then. And then to find the b value, we need to figure out the change in the interval from lower to upper limit of integration. In general, that change is what's being divided by n over here. So we have a change of 3. So the b value then is just going to be 2 plus 3, which comes out to 5, of course. Next, we need to figure out what the actual function is. So for this, I'm going to look at my basically my xi, my delta xi plus a, and see what's happening to it. So this whole 3i over n plus 2 term, what's happening here? Well, it's being multiplied by 3, and we're subtracting 8 from that. So that means that I'm going to have a function of 3x minus 8. Putting it all together, I have the integral from 2 to 5 of 3x minus 8 dx. For number 8, I'm trying to find out which of the following limits down here is equivalent to the integral from 2 to 5 of x squared dx. So I'm basically being asked to convert from definite integral to Riemann sum limit notation. So in general, I'm looking for something of the form limit as n approaches infinity from 1 to n of f of xi delta x. I need to figure out this xi so that I can plug it into f, and I also need the delta x. Out of all these, the delta x is usually the first thing I figure out. That's just going to be the change in my integral from lower to upper limit, so basically b minus a, divided by n. So in general, that's going to be b minus a over n. So in particular, we've got 3 over n for this one. So that's my delta x. Looking at my answer choices, that's going to help me narrow it down to choices b and d already. Let's keep going though. So to get this xi, I need to do a plus I times delta x. So for this one, my a value is 2. So I have 2 plus basically 3i over n. And now, I have to actually apply the f function to all of this stuff. So f in this case is just the x squared. It's your integrand. So I have 2 plus 3i over n quantity squared times 3 over n inside my summation limit notation. So in general, matching one of the answer choices, that's looking like choice D has all of that. For number 9, we're given this table with selected values for a continuous function, and we're told that the function is increasing over the interval from 0 to 3. Based on that, we want to know which of the following could be the value of the integral from 0 to 3 of this function. So this is one of those situations where you need to approximate it, but should we use LRAM or RRAM? Well, in this case, we're going to have to use both. And the key here is realizing that this is an increasing function. So that means that LRAM is going to underestimate it, and then, as we're going to say in a little bit of a time here, RRAM is going to overestimate it. But let's find LRAM first. This will give us the lower bound on what our value could possibly be. So we're going to be taking interval lengths of 0.5, it looks like, for all of these. And then we're just using the leftmost rectangle endpoints here. So we've got 0.5 times 0, 0.5 times 4, and so on and so forth for 10, 18, 28, and 40. All right, going through all of these, this is going to be 0 plus half of 4, so that's 2. This will be 7, and then, let's see, plus 9 is going to give me 16, plus 14 is going to give me 30, and then plus 20 gives me 50. So this is the lower bound. This is actually an underestimate of the true value. So that means that choice A cannot be correct. It's got to be one of these other choices. Okay, well, RRAM, we said, since this is an increasing function, RRAM is going to overestimate. So hopefully RRAM gives us an upper value that lets us eliminate some of these other answer choices. So I'm basically using 0.5 again, but now I'm going to use the rightmost rectangle endpoints. So I'm doing 0.5 times 4, 10, 18, 28, 40, and 54 this time around. So one quick way of doing this, actually, I'm not using this 0.5 times 0 anymore. I've basically replaced that on the other end with 0.5 times 54. This 0 didn't really give me anything anyway. So I've still got 50 for everything except for this last term. And this last one, I'm just adding another 27. So that's a total of 77 if we're trying to do it the clever and quick way. So this is an overestimate. That means that my answer has to be under 77 and over 50. The only answer choice that is both of these is choice B, 62.
For this problem, for a certain continuous function f, the right Riemann sum approximation of the integral from 0 to 2 with n subintervals of equal length is this expression here for all n. We want to know the value of this integral. So this one is actually a lot easier than it looks at first glance. They're giving us a definite integral, and then they're talking about Riemann sum approximations, so we're thinking we need sigma and deltas and all that stuff, but they're actually giving you the formula for the Riemann sum approximation. If they're asking for the value of the actual integral, they're basically asking for a Riemann sum that has an infinite number of subintervals. So what is this approach as n approaches infinity? Well, choosing our champion here, if we were to multiply all this stuff in the numerator out, our highest term would be a 2n times 3n, or 6n to the second power, 6n squared. So this is essentially 6n squared over n squared, if we disregard the lesser terms in the numerator. And reducing that gives us 6, choice B.
For number 11, I've got a function f that is ln of x, whose graph is shown, and we want to know which of these following limits is equal to the area of this shaded region. So this shaded region, we could express this as the integral from 1 to 4 of ln of x dx. And essentially, we need to figure out which of these Riemann sum limit notations here corresponds with what we just wrote. Okay, well, this dx, this is really the delta x in our Riemann sum notation. So this is just going to be b minus a over n, so 4 minus 1 over n, or 3 over n. Next, this x in the function here, ln of x, this is normally just a plus, let's see, delta x times I. So in this case, it's going to be 1 plus, and then we have 3 over n times k. And putting it all together, I've got the limit as n approaches infinity of the sum from 1 to n of ln of all this stuff, and we'll just write this as 1 plus 3k over n times 3 over n. What does that match here? Well, going through, it looks like this is going to give us answer choice B. A and B look kind of similar, but in B, we have this stuff inside the ln. The 1 is inside the ln. Answer choice A is the 1 is outside the ln. So we're going with choice B.